Hi everyone, welcome to the Earth Science Regents Review podcast series created by Hammock's Middle School Earth Science Department. Today we're going to focus our attention on page 1 in the reference table, your equations box. Well, this box actually has 4 different equations, and the first one we're going to deal with is going to be eccentricity. Now this is a formula that you do in astronomy, and you measure how round or how flat an orbit's going to be as it revolves around another object. Now most of the time you're going to measure a planet's eccentricity around the sun. So you're going to measure the distance between the focal points inside the ellipse, and you can divide it by the length of the major axis. So it's very important for you to set up your equation properly. It's going to look a little something like this. E equals d over L. The thing is with this, you're never going to have a unit associated with it because the units in the numerator cancel out with the units in the denominator. Now this is going to be a calculation that's always rounded to the thousandths place. So if you look at your solar system data chart in the reference table, all your eccentricities are in thousandths place values. Now you'll notice you have a very big difference between a very round orbit and a very flat orbit. Your numbers that are close to 0 have a very round orbit. Your numbers that are very close to 1 have a very flattened orbit. So when we say that an orbit is very round, it is somewhat of a non-elliptical orbit, and we say that an orbit that's very flat has a very high eccentricity and has a very highly elliptical orbit. So a big difference between those two values. The next equation is gradient, and this is basically going to tell us how steep or how flat a landscape feature is going to be. The change in field value over the distance. Now when you talk about field values, okay, it's all about the slope of the land. Okay, it's all about the fact that you want to try to figure out how steep or how flat the landscape is going to be. But if you notice here, field values is not only for elevation, you can also do it for anything that's a measurable quantity, like temperature, pressure, just kind of give you a couple examples there. Okay, the distance is going to be the horizontal value between the 2 points, so you subtract the field value, you divide it by the horizontal distance between them. What will happen here, very important for you to round to the tenths, and a very common gradient or a very common slope unit is going to be feet per mile or meters per kilometer. So those are going to be ones that are going to be very important. So when you talk about field values, a lot of times you're going to get elevation, but in many cases you can also measure the gradient of temperature and pressure as well. So the units I gave you here are distance values. The third one is going to be rate of change. This is very similar to gradient. It's a change in field value divided by time now. So a lot of times you're going to use rate of change in experimental situations. So with the rate of change, again, field value could be temperature, it could be pressure, it could be elevation, just like when you're dealing with gradient. But in this case, you're dealing with how long an experiment is going to go for. You're going to round to the tenths, and in this case, you can have a unit like degrees Celsius per minute. How much temperature change did you get over a 10-minute experiment? You can use your units as degrees Celsius per minute. The next one down, the last equation, is going to be density. And that's going to be density equals mass over volume. Now the great thing about your density is that if you set up your DMV formula in a triangle like this, you can actually manipulate it to get 3 specific variables that can be determined through the DMV formula here. So when you put density equals mass over volume, mass on top, volume on the bottom, okay, you're going to end up getting, this is your standard density formula. And your units here are going to be grams per cubic centimeter or grams per milliliter. In this one, always, all your calculations are going to round to the tenths with the exception of eccentricity. Now, if you take mass divided by density, you need to find out the volume. Okay, you're going to get a formula that looks something like this with units of just strictly cubic centimeters or milliliters because you're finding out volume. Again, you want to round to the tenths there as well. Finally, if you want to find out the mass, density times volume, the D and the V are next to each other, you're going to multiply. Mass is going to be, it's going to have a unit of grams, and again, you're going to round to the tenths here as well. Finally, percent deviation is a formula that was in the old reference table and still part of the curriculum, so it's important for us to kind of touch base on this. Percent deviation is just basically how much your measurement is off from what the actual value actually should be. So it's a measure of how much your calculation is going to be incorrect. So it's the difference between your measured value and accepted value. So you subtract the 2, divided by the accepted value. You take that whole expression and you multiply it by 100. You're going to round to the tenths, and your unit here is going to be a percentage. So it's very important for you to have an idea that when you talk about the variables, measured values are going to be your value, a student's value, or the experimental value. The accepted value, some words there that are going to describe that, are the true value, the correct value, or the actual value. So percent deviation is the difference between the measured and accepted value divided by the accepted value, multiply it by 100. So that's it with your formulas. We'll talk to you soon.